In this lecture, we will derive a well-known integral formula for the method called the method of cylindrical shells that is used for finding the volume of a solid of revolution. We obtain the solid of revolution by rotating the region that is bounded above by the graph of f of x equals y and below by the x-axis. The assumption here is that f is greater than or equal to 0. The region is bounded on the left side by the vertical line at x equals a, and on the right side by the vertical line at x equals b. Let's call this region region R. We will work on the solid of revolution that is generated as the region R sweeps around the y-axis as we are seeing on the right panel. And here we are looking at the solid at different angles and from different vantage points. To derive an integral formula for the volume of the solid of revolution, we partition the interval from a to b using the partition points x sub 0, which is equal to a, which is less than x sub 1, etc., 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 all the way up to x sub n, which is equal to b. And so, there will be n subintervals in this partition of the interval from x equals a to x equals b. We fit rectangles with horizontal tops within region R, exactly as how one would find a Riemann sum approximation for the area of region R. But instead of the area of each rectangle, we find the volume of the circular solid generated by each rectangle as it rotates around the y-axis. Each rectangle generates a circular solid called a cylindrical shell. The upper surface of each cylindrical shell is a circular ring called an annulus. When viewed from above, the annuli or annuluses, as some would say, look like tree rings or the annular rings of a tree. They are also similar to the layers of an onion that had been sliced crosswise between the root end and the stem end of the onion. For a better view of the cylindrical shells, we erase some of the cylindrical shells from the image and leave only alternating shells. Our strategy is to find a Riemann sum approximation for the volume of the solid of revolution using the individual volumes of the cylindrical shells. We turn our attention to just one of these cylindrical shells. To determine the volume of this cylindrical shell, we find the volume of the full cylinder, including the hole that's in the middle. Then we calculate the volume of the hole, which we subtract from the volume of the full cylinder. Suppose that what we are looking at is the ith cylindrical shell. Then this cylindrical shell goes from x equals x sub I minus 1 and up to x equals x sub I on the x-axis. And so the radius of the full cylinder, including the hole, is x sub I. And the radius of the hole in the middle is x sub I minus 1. We designate the thickness of the cylindrical shell, which is x sub I minus x sub I minus 1, as delta sub ix. The volume of a cylinder with radius r and height h is pi r squared h. The volume of the ith cylindrical shell is equal to the volume of the full cylinder, which includes the hole in the middle, minus the volume of the hole. The radius of the full cylinder is x sub I. Its height is equal to the y-coordinate at x sub I, and so its height is f of x sub I. Therefore, the volume of the full cylinder is pi times x sub I squared times f of x sub I. The radius of the hole this time is x sub I minus 1. We take its height to be also equal to f of x sub I, since we are using rectangles with horizontal tops for region R. And so the volume of the hole is pi times x sub I minus 1 squared times f of x sub I. We factor out pi and f of x sub I. So the volume of the ith cylindrical shell is pi times f of x sub I times the difference between x sub I squared and x sub I minus 1 squared. We factor out x sub I squared minus x sub I minus 1 squared. And so the volume of the ith cylindrical shell is pi times f of x sub I times the quantity x sub I plus x sub I minus 1 times the quantity x sub I minus x sub I minus 1. X sub I minus x sub I minus 1 is the thickness of the ith cylindrical shell, and so it is equal to delta sub Ix. If delta sub Ix is very small, so that the ith cylindrical shell is a very thin shell, x sub I and x sub I minus 1 should be very close to each other. And so we approximate x sub I minus 1 by x sub I. And x sub I plus x sub I minus 1 will be approximately 2 times x sub I. And so the volume of the ith cylindrical shell will be approximately pi times f of x sub I times 2 times x sub I times delta sub Ix. Rearranging the factors, this is also equal to 2 pi times x sub I times f of x sub I times delta sub Ix. Therefore, for an approximation of the total volume of the solid of revolution, we add up the volumes of all the n cylindrical shells. And so the total volume of the solid of revolution is approximately equal to the sum from I equals 1 to n of 2 pi times x sub I times f of x sub I times delta sub Ix, and we have our Riemann sum. Now, if f is a continuous function, and if the maximum thickness of all the cylindrical shells goes to 0, this Riemann sum should tend to a finite limit. This limit is the exact volume of the solid of revolution, and it is equal to 2 pi times the integral from a to b of x times f of x dx.